Okay, so today we're gonna finish up the section on probability. There's only really one more problem I want to go through. Does anyone need the packet from yesterday before I go on? Okay, yeah, so we're just gonna go through one more problem. There's two more problems on the packet. I'm just gonna skip the last one. I guess before I go through the next problem, I kind of went through the previous problem at the end of class pretty quickly yesterday. There's one other point I wanted to go over. The last point I wanted to go over was finding this limit of minus t over e to the t r, like t over r power. So like really we were computing the following limit. So this was the limit as r goes to infinity of minus r. I'm just going to write it as just r over e to the r over r. And so it's kind of hard to determine, at least just by looking at this function, what the limit's going to end up being, because we have something of the form of infinity over infinity, right? If you just computed this limit without any like bells or whistles or anything like that, this would give you infinity over infinity. So when you're given this situation, you want to use L'Hopital's rule, which is something we learned in Calculus 1. And so how you use L'Hopital's rule, it isn't anything super complicated or anything like that. So if we look at this limit again, this limit is r goes to infinity, this capital R over e to this capital R over lowercase r. This is the same thing as doing the limit as capital R goes to infinity of the derivative of capital R over the derivative of e to the capital R over r. So I'm just taking the derivative of the numerator and then the derivative of the denominator, not using the quotient rule, just doing it like numerator, denominator. And this will give us an easier limit to compute. So if we wanted to compute this derivative, this is just going to be equal to 1. So this is the limit as capital R goes to infinity of 1 over the derivative of this function. The derivative of e to the capital R over r is just 1 over r, or 1 over lowercase r, times e to the uppercase r over r. And then from there, you can just compute what this limit's going to be, right? As capital R goes to infinity, the only capital R we have left is this thing right here, right? So now the denominator is going to get infinitely large. So I'll just write it as, this isn't really like correct, but I'm just going to write it like this anyways. We have something of 1 over infinity, which is equal to 0. So in order to justify why this limit ends up being equal to 0, you have to use L'Hopital's rule. I'm not really sure how much it shows up. I don't plan on doing something like this on the exam, but it might show up in the homework, so I thought it was worth mentioning. So that's really to calculate what this term ended up being, right? Because this was going to infinity. And I kind of brushed over it yesterday, but I wanted to explain it in more detail because it's been a while since we've seen L'Hopital's rule. Okay, yeah, so that's all I wanted to review from yesterday. So the final problem, well, I guess there's more I want to review actually. Actually, before I continue, are there any questions about this? Okay. Yeah, so what we were doing yesterday is we were looking at probability density functions. And so where we left off, or maybe like another reminder. So what it means to have a probability density function is it's really just going to be a function p of x, such that p of x is non-negative everywhere. So like if you put in some number into p, it's going to relate to the probability of something occurring. So this means that every input we put into p should have a positive value because you can't have a negative percentage or probability. And then there's some additional properties, mainly the fact that if you take the integral of p of x over the entire domain denoted by j, it has to be equal to 1. So something has to happen. Like if you look over the entire domain, it represents the possibility of like anything occurring. So like 1 represents that something has to end up happening, like because it is certain that the value of x lies somewhere inside of this J, this domain J. And so we were looking specifically at the exponential probability density function, which is given by this piece of t is equal to 1 over r times e to the minus t over r power. And so what we did yesterday to conclude class is we were able to show that this actually is a probability density function. We took the integral of this function over its domain, which is on the interval from 0 to infinity, and we showed that the integral ended up being equal to 1. And then the last thing we did yesterday is we showed that the mean or average value of a random variable with this exponential probability density function ends up being equal to r. So this is the last thing that we did, was computing the mean of a random variable with this exponential probability density. So the last thing we'll do with this section, I don't really plan on doing too much with probability in this class, is we'll conclude with the following example. So for this example, it tells us that the waiting time t between customer arrivals in a drive-through fast food restaurant is a random variable with exponential probability density. So it tells us in the beginning, the average waiting time is 60 seconds, and it wants us to determine what the probability is that a customer will arrive within 30 to 45 seconds after another customer. And so when you're given these problems, I mean, it won't happen much in this class, but maybe in the future, if you want to determine waiting time or how long it takes for something to occur, the exponential density function is usually what you want to use to model that. And it says it explicitly in this problem. We want to use the exponential probability density function. So the first thing we want to note is that we're given that the average waiting time is 60 seconds. So what this tells us is that r is going to be equal to 60 in our probability density function. So rewriting, I mean, I already give you what the function looks like in the graph that's pictured on the left. But this tells us that piece of t, this is going to be equal to 1 over 60 times e to the minus t over 60. And so if we want to know what the probability is that a customer will arrive within 30 to 45 seconds after another customer, we compute the following. So this is really asking what's the probability that x is between 30 and 45, or maybe not x, t. And so this is going to be equal to an integral. It's going to be the integral from 30 to 45 of this p of t function. So it's going to be 1 over 60 times e to the minus t over 60 dt. And so now it's just a matter of computing this integral, which really isn't so bad. We don't have to do anything fancy with it. So we can bring out the 1 over 60 to get that. It's going to be just the integral from 30 to 45 of e to the minus t over 60 dt. And then to determine what this integral is going to be, you could use u substitution with u being equal to minus t over 60, or you can just think in terms of derivatives, like which function will have a derivative that ends up being equal to this function, and it ends up being the following. So this is 1 over 60. The antiderivative ends up being equal to minus 60 times e to the minus t over 60. So if you took the derivative of this thing right here, you would get a minus 1 over 60 that comes out in front, which would then cancel out with the minus 60. So it works out as you would want it to. And then we evaluate from 30 to 45. So you can cancel things out to make things a little bit nicer. So this is, you have a 1 over 60 and a minus 60. Those things cancel out. So this is really just e to the minus t over 60, evaluated from 30 to 45. If you plug in t is equal to 45, you have minus 45 over 60. So this is really equal to e. Oh, there should be a minus sign in front, actually. Right, because we had the, I keep on forgetting my minus sign. So yeah, she had a minus sign out front. And so this will be minus 3 over 4 power, and then that will be plus e to the minus 1/2 power if you plug in t is equal to 16. I mean, you could just leave your answer like this, I suppose, on the exam, but I mean, it's like you want to find what the actual percentage is going to be. So this ends up being equal to 0.134, which is equal to 13%. So there's a 13% chance that another customer will arrive within 30 to 45 seconds. So it's just a matter of computing this integral right here. Yeah, on the exam though, you can just leave your answer like this, even though it's not as satisfying, I guess. I like seeing the percentage. Okay, any questions about this example? Okay, yeah, so there isn't really anything new going on in this section. We're just applying what we already know, just computing integrals, except there's this new context or interpretation that we have. Yeah, so the next example, I'm not going to go through it now. I might put in the group work on Friday. It has to do with quantum mechanics, which deals a lot with probability, so it's pretty interesting. Okay, next we're going into section 8.2. Section 8.2 is the most important section from this chapter. If you're taking Calc 3 next semester, or eventually in your life, you're going to have to be able to compute arc lengths. Like, it's going to show up again. So I think, and then like the other sections in the chapter are kind of like take it or leave it. Okay, so there's kind of a long setup for like the equation for arc length, but I decided to not include it in complete detail just because I didn't want to spend 20 minutes going over it. I feel like it would double the packet if I did, and you had to remind you of like what the mean value theorem is. And I feel like you don't want to talk about the mean value theorem. But the main idea for arc length and eventually surface area, the two are related to one another, is it's just another method or technique you can use integration for in order to compute like total amount of something. So far we've used integration to calculate distance traveled, total mass, total cost, probability, so on and so forth. And so another quantity we can use to calculate, we can use the integral to calculate is the length of a curve. So this is going to be called arc length. And so the derivation of this formula, which I largely skipped, is going to be used via the Riemann sums. So we use approximation followed by passage to a limit. And so I guess the big idea, like I'll go over a little bit of it because I don't want to just say what the formula is and then just have you like memorize it. It's good to be able to, I guess, deduce these things. So like the main idea is you start off with a curve, which I'm highlighting in red right now. And then you partition the curve into intervals going from points P0 to P1, P1 to P2, and then generalizing Pi minus 1 to Pi. And so between each of these points, we can draw a line. So the line is just going to be a straight line, which denotes the length from P0 to P1, and then the length from P1 to P2, so on and so forth. And so intuitively, if we make it so these points are arbitrarily close to one another, these straight lines between the 2 points are going to look closer and closer to the curve. And so we just need to be able to determine what these lengths are going to end up being equal to. And so we can use the Pythagorean theorem to determine what these lengths are going to be equal to. So the picture on the right is really just zooming in on the picture that we had on the left, except we're just looking at two general points, Pi minus 1 and Pi, and we want to determine what this Li is going to end up being equal to. And I think this is what the reading assignment was asking you to look at. And so if we use the Pythagorean theorem on this right triangle that's formed here, where the hypotenuse is given by this Li, the height of this triangle is given by the difference between f of xi and f of xi minus 1. So like these 2 points on the y-axis. So that's this quantity we have here. And then the difference in x values is really just going to be xi minus 1. And so this is telling us by the Pythagorean theorem, I might have to squeeze, I'm going to use a smaller writing. So this is Li is really equal to delta, the square root of delta xi squared plus f of xi minus f of xi minus 1 squared. And so this f of xi minus f of xi minus 1, it's kind of close to a derivative. The derivative of a function, loosely speaking, like I don't want to go too much in detail about this. It's something of the following form. So it's like f of x plus delta x minus f of x over delta x. And so we have something on the right hand, like this term I'm circling now looks kind of like a derivative. If we were to multiply both sides by delta x, like if we multiply both sides by delta x, we would have delta x times f prime of x is equal to this difference in y values that we have. And so I'm hand waving a little bit. You should really be using the mean value theorem, but you can rewrite this square root in the following way. So the square root is really delta xi squared plus delta xi squared, or yeah, delta xi squared times f prime of x squared, right? Because we are squaring this quantity here. So if we multiply both sides by delta x, we're going to have a delta x squared times f prime of x. And so then you can, I guess this should be delta xi, and then you can factor out a delta x. So this is really delta x times the square root of 1 plus f prime of x squared. So I'm being a little bit hand wavy, but this is like the idea behind how they end up deriving what this formula for the arc length is. So like really they're using the mean value theorem, but you can get an idea of what's going on just by following this calculation. Okay, so what this is going to tell us, so now if we take the limit and make it so these points are arbitrarily close to one another, you take a sum of all of these lengths, it turns into an integral. It's like the Riemann sum idea. So what we end up getting for the formula for the arc length, so we have to assume first that the derivative exists in the first place. So if f prime exists and is continuous on the interval from a to b, then the arc length s of y is equal to f of x over this interval from a to b is going to be the integral from a to b of the square root of 1 plus f prime of x squared. So like this 1 plus f prime of x squared came from this here. But you don't have to know how to derive this on like quizzes or exams or anything. I'm not going to ask you to like derive the formula for the arc length. But maybe it helps you remember, even though you can just write down the equation on the exam anyways. Okay. And so this is the main formula. You're pretty good on this section if you just know this formula and know how to compute this formula. But we'll go through some examples because there's some techniques you usually want to employ when determining arc length. So for the first example, we want to find the arc length s of the graph of f of x is equal to 1 over 12 times x cubed plus x to the minus 1 over the interval from 1 to 3. So it's this region or this graph pictured on the left-hand side. And then this region or this part of the curve in red is what we want to compute the length of. And so what I would recommend to start off this problem is let's just determine what f prime of x is going to be equal to, because we want to determine what 1 plus f prime of x squared is equal to. So just start off small by seeing what the derivative of f is equal to. So we can just use the power rule for this derivative, right? It's just a polynomial. So this is going to be 1 over 12 times 3 times x squared. So that's 1 over 4 x squared. And then the derivative of x to the minus 1, you bring the minus 1 down. So it'll be minus 1 times x to the minus 1 minus 1. So this is minus x to the minus 2. Really, I'm just using the power rule for the derivative. And like derivatives are going to be coming back in this class, starting with chapter 9. So it's a good idea to brush up on how to calculate derivatives. Okay, and so what we want to do next is, now that we know what the derivative is, let's see what 1 plus the derivative squared ends up being equal to. And the overall goal is we want to make sure, if possible, we can cancel out the square root inside of the integral, because we don't like it when there's a square root inside of the integral. It's kind of messy. Okay, so this is going to be equal to 1 plus the square of 1 over 4 times x squared minus x to the minus 2 squared. So you can FOIL this quantity that's being squared to get that this is going to be equal to 1 plus 1 over 16 times x to the 4th power. If you do x squared times x to the minus 2, you just get x to the 0th power, which will just be equal to 1. And then you're multiplying, like you have this 1 over 4 in front. So you're really just going to have a minus 1 over 4 minus 1 over 4, which will give you a minus 1/2. And then if you multiply x to the minus 2 by itself, you'll get plus x to the minus 4. So this part is really just, I'm just FOILing out. So you can trust what I have written here, or you can FOIL it out yourself and make sure that this is what it ends up being equal to. It's just algebra. And so this ends up being equal, you have a 1 minus 1/2. So you can rewrite this as being equal to 1 over 16 times x to the 4th power plus 1/2 plus x to the minus 4. And then from here, we pretty much had what we did, or we pretty much have what we originally had, except instead of, like, if you just focus on this part, right, it's really similar. The only difference is we have a plus sign here instead of a minus sign. And we know that this part here was equal to the square of 1 over 4x squared minus x to the minus 2. So you can actually rewrite this as being equal to 1 over 4 times x squared plus x to the minus 2 squared. And then you can test and make sure, like if you actually multiplied this out, you would end up getting the following. But really, I think the easiest way of seeing it is, like, again, this part I have in parentheses is really the same as what I have underlined. The only difference is this sign. So as we knew that the thing in parentheses was just equal to this part squared, it's really just going to be a change in sign that's occurring to go from here to here. Okay, so this is nice. Like, we want to have this square because when we're computing the arc length, we're going to actually be doing the square root of 1 plus f prime squared. So then this square here will cancel out with the square root inside of the integral, which will give us something easy to compute. So once we know this, we can determine what the arc length is going to be. So we have that the arc length, this is denoted by s. This is going to be the integral from 1 to 3, because we're on the interval from 1 to 3, of the square root of 1 plus f prime of x squared dx. And we determined what 1 plus f prime of x squared was. That was this 1 over 4x squared plus x to the minus 2, all squared. And so this is going to be equal to the integral from 1 to 3 of the square root of this 1 over 4 x squared plus x to the minus 2 squared dx. So what's nice, as I said before, is the square and the square root cancel out with one another. And so we get a nice integral to work with. This is just the integral from 1 to 3 of 1 over x, or 1 over 4 times x squared plus x to the minus 2 dx. So then it's just a matter of determining what this integral is using the power rule. So this is going to be 1 over 4 times 1 over 3 x cubed plus x to the minus 1 over minus 1. And then this is all evaluated from 1 to 3. So you could leave your answer like this, but it ends up being equal to 17 over 6. If you actually plug in the numbers and simplify a little bit, you end up getting 17 over 6. So the hard part of this problem usually is just finding a way to express 1 over, like, the 1 plus f prime of x squared in a way that will eventually cancel out with the square root. It doesn't always happen, but that's usually the trick for these kinds of problems. I'll actually say this is one of the harder ones. I think it's kind of hard to see immediately that this would end up being equal to this square. You can use completing the square as well if you wanted to, but okay. Any questions about this example? Okay, so we'll just keep on going along. The next problem is a more applied problem, so it's based on physics. So just reading it out, based on physical principles, the height of a cable hanging under its own weight is modeled well using the hyperbolic cosine function from the last chapter. So we're going to suppose we have a cable hanging from two poles that are 100 feet apart. So it's going to be located at x is equal to minus 50 and x is equal to 50, which is pictured below. And then we have that the height is given by h of x is equal to 250 hyperbolic cosine of 0.004x minus 225, which looks bad, but this will end up being a really nice function to work with. And so it says, note in the middle, the height of the cable is 25 feet, and at the poles, the height is given by h of minus 50 is equal to h of 50, which is equal to 30 feet, which I don't think is actually relevant for this problem at all. So like the cable hangs 5 feet lower in the middle than the height at the poles. Cool. I don't think it's relevant at all. What matters is we have this function h of x, and we know what the beginning and the end of the intervals are going to be. So if we want to determine the length of the cable, this is really just asking us to find what the arc length is going to end up being. And you can probably guess we're using a hyperbolic cosine function. We want like a square to show up. So we're probably going to use like the Pythagorean identity. But first, let's just look at what h of x or h prime of x ends up being equal to. So the first thing we do is we just compute the derivative of h. So we have to use the chain rule for this derivative, right? So if we take the derivative of hyperbolic cosine of 0.004x, we do the derivative of the outside. That's going to be hyperbolic sine. So this ends up being 250 times hyperbolic sine of 0.004x. And then you multiply by the derivative of the inside function, which is equal to 0.00 0.004. All right, so this is just using the chain rule to calculate the derivative. And what ends up being nice is if you do 250 times 0.004, it just ends up being equal to 1. So this actually ends up just being equal to hyperbolic cosine or hyperbolic sine of 0.004x. Okay, so that's the derivative. We got it into a pretty nice form. And so next we want to consider what 1 plus the derivative square is equal to. So this is just going to be equal to 1 plus hyperbolic sine squared of 0.004x. And then as a reminder, we've seen in the past, this is like something you should just remember, or like you want it on your index card before an exam or something along those lines. What we saw in the past, if you do hyperbolic cosine squared minus hyperbolic sine squared, this is equal to 1. And so if you add hyperbolic sine to both sides, you get hyperbolic cosine of x is equal to 1 plus hyperbolic sine squared of x. And that's kind of what we have here. The only difference is we have this 0.004x. But if you just wrote this as a u instead, you'll just be saying like this would be equal to hyperbolic cosine squared of u. I'm not going to do like a change of variables. I'll just write this as this ends up being equal to hyperbolic cosine squared 0.004x. So even though we don't have like a straight up x in the parentheses, it doesn't really matter. It doesn't change this identity that we're using. This is from section, I think 7.4, if you want a reminder on why this ends up being true. It's just straight from the definition of hyperbolic cosine and sine. Okay, so once we have a really desirable form here, right? Because one, like we have the 1 plus like the square of the derivative ends up being a square itself. So it will cancel out with the square root when we actually do the square root, the arc length function. So we have arc length. This is equal to the integral from minus 50 to 50 of the square root of 1 plus h prime of x squared dx. And so we know this is equal to the integral from minus 50 to 50 of the square root of hyperbolic cosine squared of 0.004x dx. And so just like the last example, the square root and the square cancel out with one another. So we get something nice. This is going to end up being equal to the integral from minus 50 to 50 of hyperbolic cosine of x. And then you have the, not x, hyperbolic cosine of 0.04x dx. Then you could use substitution to determine what this integral ends up being. You'll let u be equal to 0.004x. But maybe you can just see immediately that this is going to be 1 over 0.004 times hyperbolic sine of 0.004x. Right? If you took the derivative of this function, you would use the chain rule. Hyperbolic sine would turn into hyperbolic cosine, and then you take the derivative of what's inside, and it would cancel out with the 0.004. Okay, and then you evaluate this from minus 50 to 50. So you can leave your answer like this, but the actual number ends up being 100.67 feet. So again, the actual integration part really isn't the difficult aspect of this problem. It's just rewriting 1 plus the derivative squared in a way that cancels out with the square root. Okay, any questions about this example? Okay. Yeah, so the next one's a little bit more interesting. It's a little bit more difficult, I would say. Maybe you can tell immediately that we can't just use our normal derivatives to determine what's going on here. So the next one, we want to show that the arc length of the asteroid x to the 2/3 plus y to the 2/3 is equal to a to the 2/3, ends up being proportional to a, where a is some number that's greater than 0. So this asteroid looks something like this. It's pictured on your packet or in your packet. This is just the case when a ends up being equal to 1. And so you can notice that this is an implicit function, meaning that on the left-hand side, we have a function in terms of x and a function in terms of y being equal to some constant. So we want to be using implicit differentiation in order to determine what y prime is going to end up being. So if we want to determine what y prime is, what we do to begin, so this is Calc 1 stuff, but it's Calc 1 stuff we haven't really used very often since Calc 1, so maybe it's a little bit rusty. So what ends up happening is we're going to take the derivative of both sides of this equation. With respect to x. And so the right-hand side of this equation is just a constant, so the derivative will end up being equal to 0. But on the left-hand side, so we do the normal derivative when we're doing the derivative of x to the 2/3 with respect to x. So this is just going to be the power rule, i.e. we'll have 2 over 3 times x to the minus 1 over 3 power. And then this is going to be plus. So when we take the derivative with respect to y, we have to use the chain rule because we're thinking of y as being a function with respect to x. So we treat the derivative of y to the 2/3 at first, just like usual. So we'll use the power rule to get 2 over 3 times y to the minus 1 over 3. But then you have to remember to multiply by dy dx, which we'll just write as y prime. So we're thinking of y as a function with respect to x. So if we take the derivative, we have to use the chain rule. So what that means is whenever you're taking a derivative with something in y, you always have to multiply by y prime afterwards. That's the practical way of thinking about things. You always just include the y prime at the end. And then the derivative of a to the 2/3 is just a constant. So that's 0. Okay, so the main goal at this point, we computed the derivative. What's left is we want to determine what this y prime ends up being equal to. So we're going to solve for y prime. The first thing we can do is we can subtract over this 2/3 times x to the minus 1/3. So this will be 2/3 y to the minus 1/3 power times y prime is equal to minus 2/3 times x to the minus 1/3. And then we'll just divide both sides by this 2/3 times y to the minus 1/3 to get y prime on its own. Right, so if we do that, we'll have y prime is going to be equal to minus 2/3 times x to the minus 1/3. And then this will be over 2/3 times y to the minus 1/3. And so you can rewrite this. I mean, there's a couple ways we can simplify this, right? We can cancel out the 2/3 in the numerator and the denominator. And then we don't really like having the minus powers. So you can actually do a flip here. So you can rewrite it in the following way. This is really equal to minus y to the 1/3 power over x to the 1/3 power, right? If we have this minus power, it really means this is going to be x to the 1/3. And then the same in the denominator. The minus 1/3 means it's like 1/1 or 1/y to the 1/3 power. So you can bring it up to the numerator. Okay, I'm gonna need more space for this. Okay, so this is the derivative. We found what y prime was equal to. After we determine what y prime is equal to, we want to do 1 plus y prime squared and see what happens. And then eventually we want to integrate that function. So this is going to be 1 plus y prime squared. This is going to be equal to 1 plus, so you can rewrite it. So this is minus y to the 1/3 power over x to the 1/3 power squared. So we can rewrite this as 1 plus y to the 2/3 over x to the 2/3, just squaring both the numerator and the denominator. And this isn't really a satisfying way of writing this. Like if we could just put this inside of the integral, but we would have an integral of the square root of 1 plus y to the 2/3 over x to the 2/3. So we want to write this in a way that's a little bit nicer. So eventually we can just cancel out with the square root. So one way of doing this, I guess I'll ask you, if we wanted to write this in a nicer form, does anyone know like what would be the first steps in doing so? And I'll say it's not like a calculus technique or anything. Like it's like a algebraic technique. When you have, does anyone? Yeah, Jessica.
Why are x to the 2 power? Are we supposed to keep the negative symbol?
Well, we were like this part right here.
Yeah.
We were squaring it. So when you square it, it'll go away. So it'd be like minus y over, or minus y to the 1/3 power times minus y to the 1/3 power. So it will become a plus. So that will go away. Oh yeah, Virginia.
Use the equation of the graph and put it in terms of x and y.
Yeah, you do want to do that. Yeah, you want to do that eventually, I would say. There's like something else I like before even doing that. I'll say there's like one other thing I'm looking for. And I'll just say it. We want to use we want to set up like a common denominator between these two things. Like if we want to add these two fractions together, we can rewrite this as being equal to x to the 2/3 over x to the 2/3. And then this will be plus y to the 2/3 over x to the 2/3. So this is really equal to x to the 2/3 plus y to the 2/3. And then this will be over x to the 2/3. Yeah, so this is why I wanted to do the substitution afterwards. So as Virginia said, we have this original equation, x to the 2/3 plus y to the 2/3 is equal to a to the 2/3. And we have this x to the 2/3 plus y to the 2/3 right here. And so we can rewrite this like x to the 2/3 plus y to the 2/3. This is just going to be equal to a to the 2/3 over x, or over x to the 2/3. Right? Like just using this original equation that was given to us in the very beginning. So we can reference back, and now we have something entirely in terms of x. We don't want to have something with y in it. Okay, and so this is nice. So you can rewrite this if you wanted to. This is the same thing as a to the 1/3 power over x to the 1/3 power squared. So now we have this 1 plus y squared, or y prime squared. We were able to show that it ends up being a square itself. And so now integrating is going to be the easy part. So now we have that the arc length, this is going to be equal to the integral from 0 to a of the square root of 1 plus y prime squared. I should write this differently. I'm gonna write it like this. I don't care. I'm just gonna, whatever. But it is with respect to x. That's like what I was kind of hung up on. So this is equal to the integral from 0 to a of the square root of 1 plus, wait, hold on. I'm not gonna simplify that much. So we already have that 1 plus y prime squared is equal to this a to the 1/3 power over x to the 1/3 power squared. So this is just a substitution you can make immediately. Squared. So everything works out. The square root and the square, they cancel out with one another. Like this. And so this is going to be equal to the integral from 0 to a of a to the 1/3 over x to the 1/3 dx. You can rewrite this as a to the 1/3 times the integral from 0 to a of x to the minus 1/3 dx. And then it's just a matter of using the power rule of integration to determine what this integral ends up being. So this is going to be a to the 1/3. So this is going to be, if you do, so it'll be x to the minus 1/3 plus 1. So it'll be x over 2/3, which is really going to be 3/2. And then x to the 2/3 like this. And then it goes from 0 to a. And so if you substitute in x is equal to a, you'll get the following. So this is going to be a to the 1/3 power times 2/3 times a to the 2/3 power. And then if you plug in x is equal to 0, you just get 0. And so if you multiply a to the 1/3 power by a to the 2/3 power, you just get a. So this is going to end up being equal to 2/3 times a, which is what we wanted to show in the beginning. We wanted to show that the arc length ended up being proportional to a. So that just means we can determine the arc length just by multiplying a by some constant. Yeah, so this one's a little bit more difficult because you have to do the implicit differentiation from Calc 1. I think there's a problem on the homework where you have to do a problem similar to this. It might even be like the same asteroid, but maybe it's just like a is equal to 1. But if that's the case, you'll just plug in a is equal to 1, and you'll be able to determine that the arc length would be equal to 2/3. Okay, any questions about this one? Okay, so I guess I'll briefly, I don't have enough time to go through another example, but I'll talk a little bit about surface area. So you can use arc length or the arc length formula to determine the surface area of a surface of revolution. So we looked at surfaces of revolutions before, but we were always computing the volume. That was like the disk and washer method and the shell method, stuff like that from chapter 6. So I guess like the initial premise is that the surface area S of a surface of revolution can be computed by an integral that is similar to the arc length integral. And this is also something they spent a lot of time deriving in the book by kind of decided to just represent what's going on in terms of pictures. I didn't want to get too deep in the weeds for this one. We're always going to be supposing that f of x is greater than 0, so the graph lies above the x-axis. And so what we're going to be doing is we're going to be looking at our original like surface or region R, and we're going to be doing an approximation of that region, which is what's pictured here. So we have like this R star, which is, it looks similar to R, except it's not going to be as smooth. So like what's going on is, maybe it's hard to see, but on the boundary, instead of just choosing like a smooth curve, we're instead going to be doing an approximation via these lines that we were doing in the beginning of class today. And so it's going to be a little bit more rigid, but as we choose points that are closer to one another, we're going to get a better and a better approximation of R. And so the big idea is that the surface area of this region here is approximately going to be equal to the surface area of some cylinder. Like if we had something of this form right here. Oops. If we make the lengths of each of these lines arbitrarily small, that means like this cylinder can be expressed, or like the surface area of this will be approximately equal to the surface area of this cylinder. And so if we let the height of the cylinder be determined by some bi on this interval, so this is like xi minus 1, this is xi here, the height is determined by some f of bi. And so if you wanted to compute the surface area of this cylinder, the surface area of the cylinder is going to be equal to 2 pi multiplied by Li, which is kind of like the height here, and then you multiply by f of bi. That's kind of the intuition behind what this following equation is going to end up being equal to. So you just have to think in terms of, and again, I'm not going to ask you to ever derive this in your entire life, but to get like an idea of where this equation is going to be coming from. So the area of a surface of revolution, if we assume f of x is greater than or equal to 0, and we have that f prime exists and is continuous on the interval from a to b, the surface area S of the surface obtained by rotating the graph of f about the x-axis when x is between a and b ends up being given by the following formula. So it's pretty much exactly like the arc length formula, except we have this 2 pi in front, and we're multiplying the square root of 1 plus f prime of x squared by f of x. So integration by parts is going to show up a couple of times, just because we have like a product of two different functions here. But this is kind of where the idea of the equation comes from, is thinking in terms of the surface area of the cylinder. So that's what we'll pick up with tomorrow. We'll go through maybe 1 or 2 examples, and then we'll move on to section 8.3. Which one? 5 point. I don't know what this is in terms of. Yeah, so it'd be pi over 6 times 5 to the 3 halves power minus 1. Yeah.
So for this one, when it's saying show that the arc is proportional to it, what did we do here so that it's proportional? Because we're just solving an integral.
That was the following, like the answer we ended up getting was this 2 over 3 times a. So this is like, this was the arc length. Like when we compute the arc length, we always get a number because it's a definite integral. And so we computed the arc length and showed that it ended up being 2 over 3 times a. So that's what it means to be proportional to a. Is like we have some number being multiplied by a. Like it's on the line of like a times x. Because that means to be proportional.
Alright,
Does that make sense?
kind of.
And I was going through this last night. I had to go back to this section where I was talking about the midpoint.
What is? Oh, is this
Midpoint, yeah. And I was talking about like the Simpsons rule and stuff. Did we know the midpoint rule?
I don't think so.
Okay, that wasn't something we learned last semester.
It may have been. I don't think so. I mean, there's like different ways of breaking up like partitions
Yeah,
to do like the Riemann sums, but we just talked about like left and point and right.
like I guess we did do the midpoint because you do the right minus the left
Yeah.
and divide by 2. Is that right?
Or like you take the sum and divide by 2. But yeah, that's what I do.
Okay.
Hi. So what we were doing at the beginning of the class when we had a lowercase r at points and we had uppercase r at
Yeah.
points. What are they like denoting that they're different, but they're both r?
Yeah, that was like, so when I do the capital R, like the reason why I did the capital R, I think it's written better in my notes than I was doing in class. Yeah, so this was, it's kind of a mess, but this was the original problem that we had. Wait, no, it's not. This is, oh, no, this is the, okay, I'm scrambled. Okay, so this is what we were looking at before. It's like if you wanted to compute this integral really, like it's integral from 0 to infinity, so you had to introduce this limit. So like we already had this 1 over r, like this lowercase r is just like some number that's greater than 0. And then I introduced this uppercase r, where r is going to infinity. Because that's like, I just use r because that's what we did in section
Okay.
7.8 or 7.7. But I probably, like there's 2 r's, but they have no relation with
Okay. No, that makes more sense. All right. Thank you.
Where does this really come from? Like 1 plus f of x squared, like why? Is that what we're computing? It comes from this.
Yeah, I mean, another way of thinking about it is as these points get closer and closer to one another, like this li is going to get closer and closer to approximating the tangent line to the
Yeah.
curve. But I mean, it's like the derivation, I think I have it written out. Oh, I have it written out incorrectly, but yeah, it's like going back to the derivation. Really just using the Pythagorean theorem initially, and then rewriting the difference of f of xi minus f of xi minus 1, rewriting it in terms like just ignoring the limit. I should have written like this is approximately equal to, but this is like the difference we have here is approximately equal to what would happen if you multiply both sides by delta x. So it's like delta x times f prime of x. And then this thing is being squared. The only thing is, like, this is like the right idea, but really we're using something called the mean value theorem, which we talked about last semester very briefly, which says that if you have like 2 points and you look at like the secant line between those 2 points, you can find a point on the curve whose derivative ends up being parallel with it. So really like I'm choosing a point between xi minus 1 and xi, such that the derivative of that point ends up being equal to this thing right here. But I didn't want to go into, I didn't want to say that much about it, but it's in the book. But this is like the main thrust of the argument. It's like this difference is approximately equal to the derivative if you were to multiply by delta x.
Thank you.
Yes.
So if we were discovering math for the first time, could you explain to me why the area of all little rectangles of the derivative graph of f of x is equal to f of x at that point?
Hold on. Yeah, what's like the formal statement here? Like what? Let's see.
So this is the graph f of x at 5, and this is the area of f derivative x of 0 to 5, and they're the same value, f of x at 5 and f the area of at 5.
Should
So like, if we were discovering, like if we were just a mathematician like the 15th century, and I'm trying to figure out, and I find out that area is equal to the point, how would I intuitively explain that to someone I'm teaching math to? It's like, you could just say that's just how it is, like they're inverses, like
Yeah, but you
multiplication
don't
and
wanna-
division, and also addition and subtraction. You know, you could just say they're inverses, that's how it is, but like, is there a way to intuitively, because I'm struggling with this.
I don't think there's like a great intuitive way, of explaining why it ends up being the case. Like it's like somewhat like a complicated argument. You have to like introduce like the Riemann sums, but like you have to talk about the Riemann sums for like arbitrary partitions of the interval. Like the proof of this, I think it's like 2 or 3 pages long. Yeah, it's like it's really long because it has to go like it goes in 2 different directions. I'm trying to think. Yeah, it's like it's something that's pretty complicated. I think there probably are explanations you can find that like summarize it, like in an intuitive way, in like a couple of minutes. It's not something I don't think I'd be able to explain it very well, like off the top of my head.
Okay. I was just wondering.
Which is like disappointing. It's like disappointing for me to say that, but like it's hard to think of like how it all interacts.
I feel like if I understand math, like the building blocks, I'll be able to